Alright folks, in this video we're going to be looking at summary of some of the ideas that you need when you're looking at a projectile motion question. So I'm kind of assuming you've already done some sort of activity on this in class to kind of get an understanding of why things work. But in summary, when you throw an object and it travels in a projectile, it will have velocities in in horizontal direction, and that velocity doesn't change. And the reason why it doesn't change is because there's nothing slowing it down in that direction. But in terms of velocity in the upward direction, the velocity is reduced because the force of gravity is actually pulling it downwards towards the surface of the Earth. And then when it reaches its highest height at this point over here, it will have a zero velocity. So in this case, it will have a velocity upwards, but acceleration is acting downwards. So the object will slow down in this direction. But then after reaching speed of zero, then acceleration is pulling it downwards. So it's going to start gaining speed in this direction. And since acceleration and velocity are now in the same direction, it will speed up going downwards. So that's the idea. So it will have speed, and the speed will keep increasing as time passes, and it will get larger and larger in the vertical direction. So horizontally then, because there's no force acting on it, in terms of the equations that you have to use in order to solve it, is just that the velocity in the x direction is always equal to the displacement in that direction divided by time. That's it. There is zero acceleration, assuming huge assumption that there's no air resistance, and because of that assumption, you can use this equation. In the vertical direction, though, there's always an acceleration acting on it. That acceleration comes from the force of gravity, or the gravitational force, and it is the gravitational acceleration, approximately 9.81 meters per second squared around the surface of the Earth. And in the vertical direction then, because you have a uniform acceleration, we're assuming it's uniform, and that the altitude isn't changing significantly, then you can use your 5 equations of motion in that direction. The time interval in the x component is the same as the time interval in the y component. So in this case, delta t is, or in this case, delta tx is equal to delta ty, which is delta t. So the delta t is the only variable that is shared between the two directions. Shifting up, problem-solving techniques, or the process. First of all, start with a system. So do your 5 steps. In this case, not all the steps are included. So I do want you to start with your step A, B, C, D, and E in order to solve the questions. So for this is step A, system diagram. Do your physics diagrams as well. So do your physics representation. This is just pictorial. You can do your word representation and all the assumptions that you need. And then for the rest, what you want to do for part D is you want to break all of the two-dimensional vectors into x and y components, or horizontal and vertical. You want to create you can use this method, you don't have to, but you can create a 2-column table, one for the x component and one for the y component. You can write all known values in their respective columns. Use the constant velocity equation to solve anything in the x component. So that's the constant velocity, that's this equation over here. And then use the constant acceleration equation to solve for the y component. So that's everything in the right side of the table here. If solving for final velocity, combine the component velocities to solve the 2D vector. We'll do an example of that, you will see. And remember that delta t, or the change in time, can be used for both the x and y component unknowns. And remember, a projectile starts as soon as it is airborne and ends right before it lands. What does that mean? Well, when we throw something, it starts right when it leaves the hand, and we kind of talk about what will happen to it when just before it lands. So a moment before, because a lot of students confuse this and they say, okay, when the object has reached the ground, its velocity is zero. Well, that's not really true, as vertical velocity might be zero for a second, even if it does reach the ground. But in this case, we're going to assume that there is no floor, and we just want to figure out the velocity at that point. So even the vertical velocity, if there was no wall here, it would still be going. So it's always the moment before. It's a huge misconception, one that I had as well when I was going through the course. But once you get a good understanding of what the questions mean and come to the acceptance, then it will not be an issue anymore. Let's look at a couple of examples here. In example 1, we got a student who travels down a water slide, leaving it with velocity of 4.2 meters per second horizontally. I'm going to highlight that. The keywords here, very important. And the student then experiences a projectile motion landing in swimming pool 3.2 meters below the slide. We have to determine a few things: determine how long the student is airborne, determine the student's horizontal displacement while in the air, and determine the student's velocity upon entering the water. Let's draw this diagram. We have a water slide, and then it kind of goes like this, and then we got this, and we got the water, and basically the student is here, all happy, and then they reach this point over here, and then they kind of travel down and hit the water. So in this case, there's a few situations here. The student here is just sliding down. We don't really care about this stage because the information that we're given is right when they get off the water slide. So we don't really care about that stage. I'm not even going to include it in my diagrams. I'm going to have one stage here and one stage here. Stage 2. So stage 1 is right when it falls off, and stage 2 is right when it lands in the water. When we're drawing the system diagram for this, we need to break down all the components of velocities. So initially, I'm going to actually label my positive x and y. And I'm going to use x and y in this situation. Positive horizontal is to the right, and positive vertical is going up. And in this case, the student has a horizontal speed in this direction of 4.2 meters per second. That's given to me. I'm going to be using fundamental units of meters and seconds, and I will highlight this. And the student will also have a vertical velocity at this point. So V1y. In this case, because the student is just sliding, at the moment that the student leaves the water slide, it's only going to have horizontal velocity right at that moment. And then acceleration is going to start pulling the student down, and it's going to gain some velocity. So right at moment 1, student will have a vertical velocity of 0. Later on, that will change, but right at the beginning, it will not be anything else other than 0. And then as student is going, they're going to experience an acceleration from stage 1 to 2, and that value is going to equal to 9.81 approximately meters per second squared. And then the student is going to displace both vertically and horizontally. The displacement vertically from 1 to 2 is here. So this is the displacement 1 to 2 in the y direction. And the displacement horizontally is from here to here where it lands. So this is the displacement 1 to 2 in the x direction. Let's make sure you understand this well. So I'm assuming that this is the reference point and this is where the student is falling from. The student will travel this much in the horizontal direction to land here. And I'm going to put a really big dot here. That's stage 2 there. And the student will, so x direction, and from the y direction is from here all the way to here. So x, y. And the student also at this point is going to have a velocity in this direction, and they're going to have a velocity in this direction. Let's see if we can fill out any of these information. Well, we already done this and this. That's fantastic. We already have the acceleration going down. Do we know the displacement going downwards? We do. That is 3.2 meters. I will put that in. 3.2. And I will also add the time from 1 to 2. I don't know what that is. And for the time, I'm not going to put y or x. The time it takes to go from 1 to 2 is the same. So actually, instead of putting it here, I don't want to make this confusing, I am just going to place it here. The time it takes from 1 to 2. Doesn't matter whether it's x or y. It takes the same amount to go in the x direction as it does in the y direction to reach the final point. Okay, and I will put a equal sign there. Good. I don't know what that time is yet, and I don't know what displacement in this direction is. I don't know any of these velocities either. And again, when the student reaches here, imagine there was no surface, they will have both vertical and horizontal velocity. So, determine how long this, oh yeah, sorry, some graphs. We need to do some graphs. We're going to do that here. Now we have two sets of graphs. One for x components and one for y components. And we're going to have position, velocity, and acceleration. Let's look at the x component first. So the student starts here. Let's take that to be reference point. Do that with blue. And the student is going to land somewhere in the right direction here, and that's positive for me, so I'm going to put a mark there. This is stage 1, this is stage 2. We know that there is, in terms of velocity, the velocity is going to start at 4.2 meters in this direction. That's consistent with this one, so it's going to stay here. 1. Velocity isn't changing. Velocity is staying the same in the x direction because there's nothing to slow it down in that direction. And that would mean that the position is also changing consistently and no acceleration in the x direction. Fantastic. In the y direction, we start at the reference point. Let's take the reference point again to be here. The object is traveling downwards. My positive is upwards. Maybe it wasn't the best choice, but that's okay. Since everything above the reference point is positive and everything below is negative, I'm going to put a point here. I'm going to see how we are going to connect it at a later time. In terms of velocity, we start at a zero velocity here, and our object is moving, starts to have a velocity in the y direction going downwards. That's opposite to the y direction, so I'm going to put stage 2 here. We are assuming that it's constant acceleration, so I am going to draw a straight line there. And in terms of my acceleration, the slope of this line is negative, and I will put a negative constant acceleration in there, and that would make sense because my acceleration is a negative value and my positive is that direction, and my acceleration is pointing in the opposite direction. In terms of my graph here, velocity here is 0, velocity here is negative, so I'm going to connect these to kind of get an idea about how my position time graph looks like, and that's a nice curve like that. And we got our beautiful piece of art ready to move on to the next stage. So this was stage A, this was stage B. Stage C is my assumptions in this case, so we're going to assume no air resistance or wind effects and constant acceleration. Fantastic. We're going to move to stage D, which is to solve part A, B, and C of the question. So the first question is asking us to determine how long the student is airborne. So we're trying to figure out how long they're in the air. I need to figure out what informations I have in the y direction and what informations do I have in the x direction. It's nice to sometimes summarize this in a table, so I will do that here. So here in the x direction, this one is a little bit easy. Velocity 1 is 4.2. Velocity 2 is 4.2. It's not changing. The velocity in the x direction is always the same, unless there's air resistance, slowing it down. Acceleration in this direction is equal to 0. The displacement, I don't know, and the time, I don't know. And these are the information in the x direction. Usually the only things I will really need is just velocity, displacement, and time, and I can use velocity is equal to the displacement over time. And all of these values that I'm writing, I'm using these sign conventions actually. Or you can just write the magnitudes if you want. It's completely up to you. I will actually write them in terms of vectors. Okay, now in the y direction, we got velocity 1, we got velocity 2, we got the acceleration, we got the displacement, and we got the change in time. So velocity 1 for us is 0 in the y direction. I'm just pulling out the information from here. Velocity 2, we don't know. Acceleration, negative 9.81 because it's opposite to my direction here. And displacement, we do know. Displacement is going downwards. My up is positive. I'm going to use negative 3.2. And the time, I don't know. The first question is asking how long is the student airborne? Well, here in the vertical set of information from stage 1 to 2, I have my information. I have my acceleration, displacement, and initial velocity, and therefore I can find the time. Let's do it. The equation that I need, the one that connects these information, is that displacement is equal to, and I'll write the values here too. Displacement from 1 to 2 is equal to velocity 1 times the change in time plus 1/2 of the acceleration multiplied by the change in time squared. And I'm just going to plug in the values. So velocity 1 is 0. That makes this whole situation a lot easier. And my displacement is negative 3.2. I got 1/2 times the acceleration. So that's 1/2 times negative 9.81 times delta t squared. And I'm going to rearrange this, and I will get delta t is equal to 2 times 3.2, 9.81. And this time will be approximately, actually I'll write the more exact value here, 0.80771 dot dot dot. So therefore the time from 1 to 2 is going to equal to approximately 0.81 seconds in two significant figures. And I will highlight this as my final answer for the first part, and I can write that as well. This is A. Let's scroll down a little bit. The next question is asking us to determine the student's horizontal displacement while in the air. For the horizontal displacement, well, I don't have to use the y anymore. I need to use the information on x. And we just found the time from 1 to 2, and that time from 1 to 2 is consistent here as well. So I am going to use that information now. So we now have velocity. We don't know displacement. We're trying to find that. So for part B, so this was part A. Part B I'll do in blue. We got the equation that V, velocity in the x direction, is equal to the displacement in the x direction divided by the time. And these are all from stages 1 to 2. So this is stage 1 to 2 and 1 to 2. And I'm going to rearrange for the displacement. And that's going to equal to Vx multiplied by the change in time. Vx is 4.2. And the time I found was 0.80771. Multiply those together on my calculator, and I will get the displacement in the x direction is approximately 3.4 meters. And I need the displacement, so that's going to be in the right direction. And I will write my right direction just like that. Now, the final part of this question is asking us, actually this is part B, to figure out the student's velocity upon entering the water. So that's velocity 2. And velocity 2 has two components, x component and y components. We need to figure out what these components are first and then combine them into one specific velocity. So we can definitely do that. We're going to do that here. Basically, we do have v2 in the x direction. We just need v2 in the y direction. We can use one of the equations, and I'm going to try to use an equation that doesn't have the change in time on it, just because what if I made a mistake here? If I use these values here, I'm sure they're coming from the question, so I'm not going to make a mistake using those. So I'm going to look for an equation that doesn't have delta t on it. The equation that I'm going to use to find this is going to be in the y direction. v2 squared is going to equal to v1 squared. So final velocity squared is equal to initial velocity squared plus 2 multiplied by the acceleration from 1 to 2 multiplied by the displacement from 1 to 2. The final velocity is what we're trying to find. The initial velocity is equal to 0 in the y direction plus 2 times the acceleration, which is 9.81 negative, and the displacement in that direction is also negative 3.2. Plugging those into my calculator, I will get that initial velocity is equal to plus or minus square root of, actually I'm skipping a step here, it's going to be 62.784, and then V2 is going to equal to plus or minus 7.923635 dot dot dot. And in this case, my up is positive. I know that velocity, that's the vertical velocity of the student at stage 2 is downward, so I'm actually going to take the negative here. So V2 is going to be approximately negative 7.9 meters per second in the upward direction, or positive in the downward direction. So you get to choose which way you want to represent that. And once I have this, I'm gonna do it. So I'm gonna have the x direction, which is 4.2. I'll draw that out. So that's 4.2. The y direction is negative 7.9236 dot dot dot. And I'm going to connect these two. And I need two pieces of information. I need this angle and I need the size. So to find the size, I'm going to use Pythagorean theorem. That's going to be 4.2 squared plus negative 7.9. Actually, I don't even need the sign here. We know that it's going down, so it's negative 7.9 dot 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 squared. V2 is equal to the square root of 4.2 squared plus 7.9 dot 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 squared. And I'm using the exact values from my calculator. And I get V2 is equal to approximately 9.0 meters per second here. And I will find the angle using tan ratio. So tan theta is equal to the opposite, which in my case is 7.92 divided by adjacent, which is 4.2. I will take the inverse tan, and when I plug that all in, I will get 62 degrees for my final answer for the angle. So to write my final answer, V2 is going to equal to or approximately equal to 9.0 meters per second. And in terms of direction is going to be 62 degrees below the horizontal. And I'm going to box my final answer here. And we're not going to do the evaluation step in this video. You can just think about what will happen if there was air resistance. How would that change the results? We are going to look at another example, and this time it is not launched horizontally. So let's look at this. Okay, we got a medieval prince who is trapped in a castle and wraps a message around a rock and throws it from the top of the castle wall with an initial velocity of 12 meters per second, 42 degrees above the horizontal. The rock lands just on the far side of the castle's moat, which is a pit of water surrounding the castle, at level 9.5 meters below the initial level. Determine the rock's time of flight, the width, and determine the velocity at impact. Let's do it. So we got a castle wall. Let's say this is it. And let's say we got the moat. And let's say that the rock was launched from here. This is stage 1. And it's going to travel. And it's going to come here. And we're going to call this stage stage 2. Or event 1 and event 2. Each one, in terms of my system diagram, well, I'm going to draw it out first. This is kind of the speed. And this is going to have a horizontal component. So I'm going to call that V1x. And it's going to have a vertical component. I'm going to call it V1y. The value of the speed here is 12. And the angle here is 42 degrees. I have all the information here. Fantastic. Let's look at the final stage. In the final stage, it's gonna land something like this. It's going to have a vertical component. I'm going to call that V2y. it's going to have a horizontal component, v2x. My acceleration, it's going to be in this direction, and that's the acceleration from 1 to 2. That's going to equal to 9.81. I have to take one side to be positive and one side to be negative. Doesn't really matter. I'm going to take up to be positive and right to be positive. So that's x and y. And my units, meters and second, are going to be I'm going to be using fundamental units here. Okay, some more information in here that I want to use. One of them is the displacement in the x direction. So displacement in the x direction is going to be from the reference in the x direction. That's going to be here. That is delta d in the x direction. And that's from 1 to 2. And also, there's going to be one in the y direction, which is going to start from 1 and end at 2. This is the change 1 to 2 in the y direction. Actually, I'm just going to replace this with 1 to 2 in the x direction. Just events first and then direction after. Good. And then there's going to be the change in time from event 1 to 2. And that's going to be the same. It takes the same amount of time for the ball to go from here to here, whether we look at it in terms of vertically or horizontally. Okay, I believe all the informations are shown now, so we can go ahead and draw out this situation. Okay, we're going to have position, velocity, and acceleration, and we're going to do it for the x direction and the y direction. So in the x direction, we can see that the object starts here. It moves in this direction, in the x direction. Its velocity isn't changing because in terms of velocity, we know that if there's no air resistance slowing it down, it will just keep going. So if there was no water here, it would just keep going in this direction forever. Let's take the reference to be right at position 1, and basically for the position, it just moves to the right. The right is positive, and therefore it's going to land somewhere here at stage 2. For my velocity, velocity is initially in this direction. That's positive, so it's going to be somewhere here, and it's going to be consistent. That velocity isn't changing because we don't have any acceleration in the x direction. And if that's the case, the position is going to change just constantly. So the slope of that line is going to be constant because the acceleration is constant and positive. Okay, in the y direction now, in terms of position, if I were to take the reference here, we start here. And after some time, it's going to reach its maximum velocity. You can see that that's in the positive direction relative to the reference point. And then at some point, it reaches back to the reference point right about here, and then it goes below the reference point. So this is stage 1, this is stage 2. And something's going to happen in between. We'll see it soon. And this is kind of the maximum height, and this is, okay, there we go, good. Just so that we have an idea about how to draw this out. In terms of velocity in the vertical direction, initially it's going to have some vertical velocity in the positive direction. So we kind of start here. Oh, I'm going to draw that with blue. And then as it reaches to the maximum height, its velocity, it's going to slow down, and then it's going to speed up and get faster and faster in the opposite direction. So it's going to reach a velocity of 0 here, and then speed up, 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 up in the negative direction, which is opposite to our positive. Finally, for the acceleration is constant and it's negative. So acceleration goes like that. And finally, to complete my position time, velocity initially is positive, velocity is 0, velocity is negative, and it gets steeper and steeper. So we kind of connect it. It's a nice parabola, just like that. And our assumptions here, we are going to assume a few things. Actually, I'm going to leave the parts of the questions here. Assume that there is no air resistance or wind effects, and that there is a constant acceleration. There's a constant acceleration, and we're assuming there's negligible air resistance, so very, very small and tiny. This value we do have from the question. I'm just going to go back and make sure we have everything from the question. We have the 12 meters, 42 degrees above the horizontal, and level 9.5. So this displacement in the y direction is equal to 9.5 meters. Okay, first things first, determine the rock's time of flight. Okay, that's not a problem. So before doing that, I'm going to go and write down all the information. And I'm going to go back and forth a little bit here. But actually, I do need the information here. Good. We're going to have information about x and y. In x, v1, v2, acceleration, change in time, change in position, and v1, v2, acceleration, change in time, and the displacements. Let's put on the values that we have. For velocity 1 in the x direction, that's this component over here. This component is adjacent to the angle. And since it's adjacent, we multiply the hypotenuse by the cosine of 42. So this is 12 cosine 42. And the other component, velocity 1 in the y direction, that's going to be 12 sine 42, because this is same as this, and this is opposite to the angle. For velocity 2, v2x is not going to change. That's going to be 12 cos 42. For v2, we don't know what that value is. For acceleration in the x direction is 0. We're assuming that there is no air resistance, so nothing's slowing it down in that direction. And acceleration in the other one, 9.81. The change in time, I don't know. And the change in position in the x direction, I don't know. But the change in position in the y direction, I do know. That is negative 9.5. And I know that because it's saying I know it's negative, sorry, because it's from 1 to 2. And since it's 1 to 2, it's going down, and my positive direction for my sign convention is up. So I have to choose a negative value. Now the first question asks for the time of flight. So I'm going to zoom in a little bit here. So for time of flight, I'm going to look at my vertical, and in my vertical I have one set of information, two and 3, so I can find the change in time. And for the change in time, I am going to use this color. I'm going to go with purple. And the equation that I need that connects these is that displacement from 1 to 2, so we're getting an arrow here, is equal to, and this is in the y direction, velocity 1 times the change in time plus 1/2 of the acceleration from 1 to 2 multiplied by the delta t squared. And okay, so excellent. So I have to do a quadratic equation here. So delta d 1 to 2, that's negative 9.5. That's going to equal to v1, which is 12 times sine 42 multiplied by the change in time plus 1/2 negative 9.81 and delta t squared. Okay, I'm going to get negative 9.5 is equal to, here I have 8.029 delta t minus 4.905 delta t squared. I'm going to rearrange this so I have all of the variables on one side. So I'm going to add this to both sides and subtract this to both sides. And I will get 4.905 delta t squared minus 8.029 delta t minus 9.5 is equal to 0. And what I have now is a quadratic equation where this is my a value, this is my b value, this is my c value, and delta t will equal to negative b plus or minus b squared minus 4ac over 2a. And you can do this, you can plug in the numbers now. A will be this, b would be negative 8.029, and c would be negative 4.9. So we can either do that or use your calculator to find it, completely up to you. And by calculator, I mean you can just, some calculators will actually take the quadratic equation and give you the roots. That's what I will do, but you can plug it in and you should get the exact same answer. So using a scientific calculator, delta t is equal to either negative 0.796 or positive 2.433. And it can't be negative change in time, so this is going to be my final answer. But I do need to express it in proper number of significant figures, which in my case is 2. Part B asks us what is the width of the mote. So in this case, the width has to be the total displacement in the x direction. And the next question asks us for the velocity at the impact, which we will do. So let's do this part here, part B, that is asking us the width. So that's the displacement in the x direction is what we need to figure out. We know that in the x direction, velocity is equal to the displacement over time, and that's the only equation we use from the x direction because acceleration is 0, and the displacement is equal to the velocity multiplied by the time. Velocity for us is 12 cosine of 42 degrees multiplied by the change in time, which I found from last part to be 2.433 ... And plugging these into my calculator, I will get 21.7. So I just need it in two significant figures, so that's 22 meters. And that's in this direction. But the final answer is just asking for the width. Don't need any other set of information. We don't need any direction, so that's 22 meters approximately. Finally, we need the velocity. And to find the velocity, the final velocity, we need the velocity in the y direction and the x direction. We already have the x direction, which is fantastic. We just need the y. So I am going to zoom out a little bit, and we are going to use the equation that doesn't use the change in time to find our velocity here. And let's do that using red. So for part C, we know that final velocity squared in the y direction is equal to v1 squared plus 2a delta d. I'm trying to find v2, so that's v2 squared is equal to 12 sine 42 degrees squared plus 2 times negative 9.81 times the displacement, which is negative 9.5. Plug that into my calculator and I get v2 squared is going to equal to 250.86. And if I take the square root of that, I get plus or minus 15.83868. And in this case, in terms of direction, I'm going to go back a little bit. You can see that for our velocity here, the direction in the x direction is same as our positive convention, but our direction downwards is, our direction in the y direction is opposite, so I have to use the negative here. So the velocity 2 is equal to negative 15.8, and I will use the exact values on my calculator when I'm doing the rest of the question. So I have all the information that I need. In order to combine them, I am going to use the x direction. I know that in the x direction it's going in the positive x direction, and the velocity here was 12 cosine of 42, and in this direction it is negative 15.8. Connect the two, find this angle, and find this magnitude. To find the magnitude, v2 squared is equal to 12 cos 42 squared plus, I'm just going to use positive. This is 15.8 squared. Again, use the exact values. Find the value and square root it here. And when I take the square root of the value that I get from the addition above, I get 18.17.6. So I'll leave it as that. And for my angle, tan theta is equal to opposite over hypotenuse, which is, adjacent, which is cos 42 here. That's 12. And when I take the inverse tan of that, I get 60.6189. And to represent my final answer here, I'm almost done. Velocity 2 is going to be approximately I'm writing my final answer to two significant figures. That's 18 meters per second. And for my direction, it is 61 degrees below the horizontal. And that is my final answer. Let's just review the steps for these types of questions so you have a little bit better idea. I'm just going to bring everything into a nice picture here. So Basically, when you're solving questions like this, you have to draw it out first. Usually at this level in grade 11, I will try to give you questions that are uh, 2 stages when it comes to projectile motion. When it's horizontal or vertical, you can expect 3 stages or more, but in horizontal motion, usually 2 stages. So you will then draw out the system diagram. You will draw the position, time, and velocity time graph for the situations. This is a good way to organize the data. So after your assumptions, you can write all the information you have in the X and Y direction in a nice table. Make sure you're using your sign convention when you're doing these. Once you're done that, then you're going to go to stage D and just solve for whatever you don't know. And in this case, a lot of times you're asked to find a change in time, and you do that by the information you have here. And then you can always use another set of information to find the other informations. But use whatever you have in order to find the other set of informations. And that's it. And for final velocity, that's usually the more challenging situation, unless I give you the final velocity and somehow I ask you for the initial velocity, that's also a possibility. But whenever you have, what you have to do basically is to find the two components, x or y, and once you have them, you're going to combine them and you are going to make it into the actual velocity with the proper angle, which gives us the direction. I hope that the video was helpful and have a wonderful day.